All right, so we are finally at lesson 22. So we're actually almost done with everything. We've moved into trigonometry. And so earlier today, we talked about using the unit circle to find trigonometric values. Now we're going to kind of do the same thing, but in reverse. So you see this trigonometric inverses, right? And some identities as well. We're going to do both of those. Inverses are pretty straightforward. You're actually going to read the unit circle or whatever it is that you're working with backwards. Okay, so for example, you have a circle here. And if we said find the value where sine is equal to, I don't know, let's say 1/2. Well, then you would use the inverse sine. So like inverse function, little -1 of 1/2. And you would look at the circle and find where the y value is 1/2, which happens at pi/6, or what is it, 30 degrees. Okay, so however you want to look at it, that's basically what we're doing today. Okay, so now let us do some examples here. And we'll start off with finding the value of the inverse cosine, right? The inverse cosine of the square root of 2/2. Inverse cosine of the square root of 2/2. All right, so we want to picture the unit circle. If you need to draw it out, you can, but you might be able to picture in your head. You know that this point right here, which is at pi/4 or 45 degrees, is where you'll have that square root of 2/2, comma, the square root of 2/2. And cosine, we're referring to the x value here. So pi/4 or 45 degrees would be our answer here. Okay, so let's also though talk about the fact that you do realize that cosine is square root of 2/2 in multiple places, right? It happens here as well at -pi/4, right? You have square root of 2/2. The y value is now negative, but that x value is the same. Okay, so what's important to realize when you're dealing with these inverse trig functions, if they do not specify where you should be looking, what quadrant or what interval you should be looking at, you want to, for cosine, consider the interval from 0 to pi, or 0 degrees to 180 degrees. Okay, so in other words, this region here, from here to there, you can cover all your x values in there, and we're going to just ignore the bottom half of the graph. Okay, so that's something to remember for cosine. For sine, let's do cosine, sine, and tangent. For sine, you want to cover all your negatives and positives on the y value. So you need to start down here and go up to, let me do a different color. Go up to here, right? So from -1 to +1, you're going to cover all your y values there. And the usual values we use for the radians would be -pi/2 to pi/2. Or in other words, -90 degrees to 90 degrees. And then finally, tangent. If we're dealing with tangent, you want to use the same thing that you're using for sine. Okay, so from here to here, but you do want to be careful because remember what tangent is, right? Tangent is y/x. So you want to avoid where x is 0. Nope, that's not where x is 0. X would be 0 here and here. So let me maybe backtrack a little bit. Open circle there, open circle there. So practically speaking, there's not going to be really anything different there. It's just -pi/2 to +pi/2. But this time, no endpoints, okay? So I want to keep those ranges in mind as you're working through these. Okay, here's another type of question altogether, okay? Cotangent of the inverse sine of -3/5. Okay, so let's consider what this information is giving me. First of all, we know we're dealing with inverse sine, so we're going to restrict ourselves to this region right here, this part of the unit circle. And we also know that it's a negative value. So really, I'm going to restrict myself to the fourth quadrant altogether. That's the quadrant I'm looking at. So I don't care about anything outside of it, just that fourth quadrant. Okay, so now what's happening in that fourth quadrant? Well, if you draw an arrow or a line out, a line segment, make your 90-degree angle with the x-axis. Remember, sine is opposite over the hypotenuse. So the values given to me are opposite and hypotenuse. So here's the angle, opposite, hypotenuse. Oops. Okay, you might want to say this is a -3 right here, just because then you'll remember that you carry over the negative for any y values. Okay, but I'll leave it for now. Okay, and so this is a right triangle. I'm trying to find cotangent of this angle. Okay, cotangent, you may remember. Let me not use x. Cotangent is going to be adjacent over opposite. Adjacent over opposite. So it's the same thing as tangent, but flipped over. Okay, well, I don't know what the adjacent side is. I have to find that. Opposite side, though, is 3. To find the adjacent side, I'm going to use the Pythagorean theorem. A squared plus b squared, right? This time b is 3, equals c squared, the hypotenuse squared. A squared plus 9 equals 25. Subtract 9 from both sides, I get a squared is 16. So a is positive and -4. Of course, it's going to be a +4 right here. Okay, so to find this answer then, cotangent is adjacent, +4, over opposite, which is that -3. So -4/3. Okay, use this interior part to first set up the triangle, and then find this like you normally would, based on that triangle. Okay, and so we did talk about this a little bit, but here are some basic trig identities. We'll do a few other ones too in a little bit. But you'll see sine is 1 over cosecant. Cosecant is 1 over sine, right? Of course, the same thing. If they're reciprocals of each other, then they're reciprocals of each other. Okay, you have cosine, which is the reciprocal of secant. And tangent is sine over cosine, or you could think about it as the reciprocal of cotangent. Same thing is true with cotangent. It is cosine over sine, or just the reciprocal of tangent. Okay, so of course, I don't expect you to memorize all this just looking at it, right? Just keep these in mind. Some that we haven't talked about yet are even and odd identities, okay? And remember, we did talk about even and odd functions, right? Remember what this means? Not that, there we go. This would mean even, and this would mean odd. Well, notice something, right? If you plug a negative angle in, the negative seems to transfer to the outside. It's not really moving to the outside, but it's as if you took sine and made it the opposite by putting a negative in the front. Sine is an odd function, right? It actually obeys that rule. Cosine, a negative inside, the negative disappears altogether. That would make it an even function, right? So these are even and odd identities because, well, you see, it happens that way. Okay, and so we'll use those identities and do these next couple of examples here. So let's simplify these 4 expressions. And I'm just going to do multiple steps that hopefully all make sense together. Okay, I want to find, what is this going to be? Is it going to be secant of x? Is it going to be negative secant of x? All right, that's what I'm looking for. So let me revert back to the basic identities. We said that secant is the same thing as 1 over cosine. So these 2 expressions are equivalent. 1 over cosine is the same as secant, as long as the angle stays the same. Okay, and we just looked at the even and odd identities. Since cosine is an even function, the negative basically just disappears. The negative inside has no impact on the function as a whole. So negative inside, no negative at all, same exact function. Okay, finally, 1 over cosine is just secant. So it turns out that secant of negative x equals secant of x. So you can use that identity, right? If you're working out a problem and for some reason you end up with secant of negative x, you can just completely ignore that and just change that x to a positive and keep working with it. You'll still get the same solution. Okay, let's work out tangent. So tangent is sine over cosine, keeping the angles the same. Okay, with the even and odd identities, sine was the odd one. So we know that the negative is there, it just comes out, so to speak, right? Remember, the negative inside changes the function to a negative altogether. Okay. Cosine is an even function, so we know the negative is just going to have no impact on the function at all. So cosine of negative x and cosine of x are going to be equivalent. They're the same. So I have negative sine of x over cosine of x. Notice the angles, of course, are the same. So I can write this again as negative tangent. So it turns out that changing the negative inside of tangent makes the whole function negative, right? It's the opposite of the original, if you want to think about it like that. So tangent would then be odd. Secant's even, tangent is odd. Okay, let's try cosecant. Same thing, right? So cosecant is 1 over sine. We already know that sine is odd, so we could pull the negative, put a negative on the outside there. So that's negative 1 over sine, which of course is just negative cosecant. Right? Once you know what you're doing there, it's pretty easy to run through them. Okay, so that would make cosecant odd as well. Cotangent, now I could do cosine of negative x over sine of negative x. That's one way to work it out, but let me change it up a little bit since I did that with tangent. Let's say it's 1 over tangent. It's another way to look at cotangent. We already know that tangent is odd, so the negative forces the tangent to be a negative, forces the function to be negative. And 1 over tangent is cotangent, and the negative is still on the outside. So there we go. It's as if the negative inside got transferred to the outside. In other words, cotangent is odd as well. Okay, so cosine and sine are the two even ones. Sorry, cosine and secant are the two even ones. Sine, cosecant, tangent, cotangent, those are all odd. Okay, so those are the even and odd identities. Okay, probably the most important identities that you're going to come across would be the Pythagorean identities. It's called that because it looks very much like a squared plus b squared equals c squared. And actually, that's where these identities come from in the first place, but we're not going to worry about deriving them today. So cosine squared plus sine squared is equal to 1. This could be rearranged if you need it to. You could subtract cosine from both sides, and you end up with sine squared is 1 minus cosine squared. So if you needed to convert, let's say, something that's already sine to a cosine, you could use this identity. And the other way around, if I subtracted cosine, I'm sorry, if I subtracted sine from both sides, I would get this expression here. Okay, so that is one expression, that's one expression. They all come from the same identity. All right, and the same thing is true for these. Of course, I'm not going to worry about rearranging those, but you can imagine if I wanted to get tangent squared by itself, I could just subtract 1 and I'd get that expression there. All right, so all of these are good to know, to have in your mind. Anytime you see cosine squared or sine squared or tangent squared or any of these in a problem, you should at least think about these identities as maybe making your problem easier. Okay. And then I think the last identities we'll go over, maybe not, I think so, are the double angle identities. Again, I don't expect you to be looking at these and memorizing them all right now, right? But I want you to be familiar with them because they're good to know. So this happens if you have again, double angle. So inside of your function, your trig function, you have 2 times an angle or 4 times an angle, right? It's double something. If that happens, you can just rewrite it like this, right? Where you notice you cut the inside part in half. So they're just 1 thetas. Okay, cosine of 2 theta, you have that. There's actually 3 different expressions you can use. Any one of those 3 would work. I'm going to use one in a little bit. Okay, but again, notice what it does. It takes that double angle and writes it as a single angle, right? In every single expression, that theta just became 1 theta. And then the same thing is true with tangent. So this is our expression for tangent. All right, so let's do the last couple of examples here. I think we have 2 more. You want to rewrite the expression in terms of a single trigonometric function here. All right, so in other words, I want it to have just sine or just cosine or just tangent, like one function, okay, nothing else. All right, but right now it's written as 2. And so you really just want to play with it and see what you can find. Anytime I see cosecant or something like that, like I see this in the denominator here, I'm going to go ahead and rewrite it. I'm going to write that as 1 over sine. So this is cosine squared x over 1 over sine of x. Here we go, dealing with a fraction on the bottom again. So we're going to multiply by the reciprocal. So this really becomes, I'm just do it off to the side here, cosine squared x times sine of x over 1. All right, so it's cosine squared times sine. All right, sine first. Okay, so now this didn't help me that much, but I see that cosine squared, and I did say a second ago that if you see cosine squared or sine squared, anything squared, think about the Pythagorean identities. So I have sine and cosine squared. I go back to my Pythagorean identities. Cosine squared can be rewritten as 1 minus sine squared. That would take cosine and write it as sine. Cosine squared can be rewritten as 1 minus sine squared x, right? That's the Pythagorean identities. Oh, look, we have it all written out as sines, right? So I probably could leave it like that. I'll just distribute it just to make sure I work this problem out all the way. Sine x times 1, of course, just sine x. Sine x times sine squared x would be sine cubed, right? So the little 3 would go there. All right, last example here. Let's use the double angle formula, all right, the double angle identity to rewrite this one. All right, well, let's look at the double angle ones again. Let's take note of this first. 1 minus 2 sine squared 7 theta. 1 minus 2 sine squared 7 theta. If I look at the double angles, I see something oddly familiar right here. That looks very much like our example. Only thing different here is we have a 7. Okay, well, we can work with that. Imagine this is 1 theta. If I wrote it as a double angle, it becomes a 2 theta. It doubles. So if I had a 7 theta here, if I were to double it, I would end up with a 14 theta. That's literally my entire thought process. Cosine of 2 theta equals 1 minus 2 sine squared theta, 1 theta. So if I were to go and double it, make this 7 theta, then again, doubling it would give me 14 theta right here. So this equals that. So my expression rewritten is cosine of 14 theta. And that is that. Okay, let me go ahead and stop recording.